Hello, everyone. Welcome to Biostatistics, Bio 347. Today and right now, we're going to look at the mean difference between two groups and, in particular, continuous data. So there's actually many ways you can look at two groups, and they can be frequency data, count data, etc. But we're just going to look at continuous data. And the reason why is there's a number of sort of classical tests you'll see out there, and you should know what they are. And the reason why there are so many tests just dealing with two groups and continuous data is that's sort of the classic experiment is control versus a treatment group. So you'll see a lot of those, and you should know what they are and know how to do them. All right. When looking at analyzing data, and this is generally true for any data set and specifically true for looking at two groups, you should decide if you are hypothesis testing or modeling. The difference being is if you are hypothesis testing, you're only saying, are my two groups different, period. Okay. A modeling approach is a little bit different in that you are modeling the effects and you are actually interested in how the groups are different from each other rather than just sort of broadly saying, are they different? So these are philosophically very different, and computationally, you're doing something different as well. All right, so sort of let's tackle hypothesis testing first. And there's a bunch of classical tests, and which one you use will depend on the nature of your data. Just run through a few. There's the student's t-test, Welch's t-test, the Wilcoxon Mann-Whitney u-test. There's the paired sampling, Wilcoxon paired sampling, and the Sine rank tests. Okay, so there's a whole bunch of tests, and what you need to know for the exam and for your labs is when to use each one. Okay, so let's get started. So the student's t-test. Okay, the student's t-test is what I think of as like a very simple statistical test, and it's very intuitive. So in the student's t-test, you're going to get something, a statistic that's t. Okay. And I often will say that most statistical tests boil down to a signal to noise ratio. Well, if you're looking at two groups, so let's do an experiment here. If you're looking at two groups, and we can plot their means and the variation around the data. Okay. And you want to know, despite this overlap, are these differences meaningful? So what we're going to look at is a signal, which is the difference in the means, right? So let's say it's signal, right? Because we're interested in the mean effect. And then the noise is sort of the cloud, okay? And we'll put that together and say that's the noise, okay? So very intuitively, this is how you should think about the t-test. So the signal, right, is the difference between the means. So we can say just x1, the average of x1 minus the average of x2, okay? And so t will be larger when this difference is larger, okay? But we have to account for the variation, okay? And the student's t-test looks at the standard deviation of the difference, okay? So what you can think of is the overall mean and the standard deviation of that statistic. All right. So the way to think about this is the larger the effect size, so the effect is the difference in means, over the cloud of data, okay? Over the cloud of data, right? And if there's enough overlap, that is the noise increases, it'll drown out this. So the larger the cloud, right? The weaker this signal. So we can draw the same effect size. Okay, so imagine, but now you have very tight data, right? So there's barely any overlap. This will, of course, be more likely to reject the null hypothesis. Take the same effect size, right? So this is the difference, but let's increase the noise, right? And then we're not sure because this is our estimate of the mean, right? This is our estimate of the mean, but yet the actual means may overlap considerably, okay? So in this one, we're very unlikely to reject our null hypothesis. In fact, let's go ahead and state what our null is. The null hypothesis, right, is that our means, right, are equal. In a one-tailed test where you suspect one group, you have good reason, is that, you know, we can say that mu1 will be greater than mu2. And if you're in the Pokemon, that's not true. All right, and then a two-tailed test, all you're gonna say is that mu1 is not equal to mu2, okay? So this is a two-tailed test. A one-tailed test would be greater than or less than, but it'd be one of these, okay? You should actually state that in your intro or in your methods, but somewhere it should be stated whether you're doing a one-tailed or two-tailed test. Okay, so when you test this, it would be, and you have, here are some assumptions. One is that your data are independent. So the observations within each group are independent, right? And then the observations between groups, of course, are independent, okay? So if you were looking at heart medicine and looking at the effect of reducing blood pressure, this would be one group of people and this would be a very different group of people, okay? The student's t-test assumes that the variances are equal, okay? And if all this is true, your degrees of freedom, okay, your degrees of freedom are N1 plus N2 minus 2, right? So it would just be your total sample size minus 2, okay? But you have to meet those assumptions, okay? You have to meet those assumptions. All right, so what if we don't? Well, let's tackle one of the assumptions. What if your variances are unequal? Okay, if the variances are unequal, you're going to do a Welch's t-test. And here the assumption is that this is all you know, that the variances are not equal. How do you know they're not equal? Well, the previous lecture, we went over that. So you would do an F-test. It's called an F-test, and R, it's called var test, and you would test it, okay? And if the F-test is significant, it means that these are not equal, and then you have to do a Welch's t-test, okay? A Welch's t-test is just like the student's t, except the standard deviations are not pooled, okay? Since they're not pooled, you lose another degree of freedom. And in fact, the degrees of freedom are estimated, which is something I don't understand. But it's something that R will do for you automatically, which is nice. So you don't end up with a nice integer, you end up with some degrees of freedom that's about what you expect, but usually has decimal places following. It's something I don't understand yet. All right, with Welch's t-test, I think that's, we end up with the same hypotheses, right? The same null, that the groups are equal, the same alternative hypotheses, and you should understand if you're doing a one-tailed or a two-tailed test. The big thing is, the big difference is that you haven't met that assumption that the variances are equal, and that'll change your degrees of freedom, okay? And you lose a degree of freedom because you have to treat the groups differently and you're doing an extra estimate. So you always lose degrees of freedom when you do those calculations. All right, so the student's t-test has two assumptions: equal variance and that the data are normally distributed. What if they're not normally distributed? Then you do a test that goes by various names, okay? I'm gonna kind of combine everything together. I'm gonna call it the Wilcoxon Mann Whitney U test. And with this, you get a U out, okay? That's your test statistic. So student's T and Welch's T, you get the T statistic. With a U, you get the U statistic, okay? So this test just used to be called the Mann-Whitney U test. I'm not sure where Wilcoxon came in. I wish we would just call it the U test. And the way this test works is, let's go back by example. It converts your data into ranks. In that case, let's just say your data looks like this. Okay, and we'll throw in an outlier. And what you do is you rank. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? If these groups are equal, even though they're not normally distributed, right? If the means, right, are equal, then, and let's say symmetric, then if you add up the ranks, then they should be about equal. So this is going to compare the ranks, right? So we call that a rank transformation. When you take your data, you order it and just rank it, okay? If they're equal, then the rank should be about equal. If you have more data occurring above the other, then these will have smaller numbers than these numbers, right? So if you add up this compared to this group should have a smaller number, okay? It also depends on sample size. And if you look up the equation, which I won't ask you to know, for the Wilcoxon Mann Whitney U test, ridiculous. I forgot where I was going with this. There is an adjustment for sample size, right? Because if you just have more samples, you're gonna have more numbers that add up, but there's a correction for that. All right. So I mentioned before that there were two assumptions. There's actually three assumptions. And the third one was that your data are independent from each other. Okay. What does that mean? So in the student's t-test, I gave an example of an experiment where you're looking at heart medicine and looking at blood pressure. If your data are independent, you have two different groups of people. So you have, if you had 40 people in one group, you'd have a total different set of people in the other group, okay? And they're not interacting. Paired sampling is when the experimental groups essentially serve as their own control. So for example, you have 40 people, you take blood pressure, their blood pressure before the treatment, and you measure it after. Okay, so what would this look like? So let's do this, set it up. So you have, let's say we're lowering blood pressure and we only have 4 subjects. Okay, we'll call it 1, 2, 3, 4. So it's not their ranks, it's their, we'll call it their ID number. So we can identify individuals. And what we're looking at is this difference, okay? So let's put arrows on this, okay? So we're gonna look at this difference where in a student's t-test, an unpaired test, okay? What we're interested in is this group and its noise, this group and its noise, and the difference between the means, right? So what we're doing is we're really looking down, okay? And then comparing the means. This one, we're actually going left to right and then looking down, okay? When I say looking down, I mean the noise is generated looking down, and then looking across the difference between the means. Here, you're not interested in the mean of this group or the mean of this group, okay? What you're interested in is the mean difference, okay? Here, the assumption, right, is that for a student's t-test, is that data are normal, and we'll make the means a little bit different, and the data are normal, okay? Where this, it actually doesn't matter. What you're interested in is, right, is that the difference is normally distributed, okay? So in this case, all our numbers would be negative because they're all going down, okay? So this usually paired tests are a little bit more powerful, okay? Statistically speaking, more powerful. And it also saves money. Why? Because if you're doing a student's t-test where the data are independent, you need twice as many subjects. You need a group of 40, you need a group of 40. If you're doing a test on people, you may have to house these and pay them, right? And a paired test, you have 40 people and you have a before and after. COVID tests, you actually have both. You have a group that get a vaccine and then you get a placebo group, but then you follow each one per time. So that's another layer to this, right? Which is interesting. All right, so paired test. Yeah, so the paired test only looks at the difference, right? The distribution of the differences between your subjects. And the subjects are not independent. So somebody with high blood pressure going in, very high blood pressure, even though it goes down, still is relatively high. Those with low blood pressure, even if your drug works and has low blood pressure, it'll be even lower, right? So, and how do you test the normality in this? You can do the QQ plots. You can do a Levine test. There's a number of, a Lilly-Forrest test. You can do a number of tests or just look at a histogram of the differences, okay? All right. So, again, the assumptions of this test, that your data are normally distributed. We broke the rule that our data are independent, okay? So it doesn't mean you're stuck if your data are not independent. It just means you have to adjust what statistical tools you're using. So there's two more classic hypothesis tests. And with the paired sampling, what would be your null? Okay. Your null is that the change in mean is equal to 0. Okay. And that is, let's say before and comparing your mean after, that is 0. That's the difference. So you are actually comparing that your means are the same. Okay, it's just another way of expressing it. All right, let's get rid of that. All right, so your data are dependent, so we have paired sampling, but now the difference between the two groups are not normally distributed. Are you stuck? Nope, you've got tools, okay? One is the Wilcoxon paired test, okay? The Wilcoxon paired test is a non-parametric, so let's put down two of them. The Wilcoxon paired test. And then a Sine rank test. Okay. Use the Wilcoxon rank or paired test, which is, it does use ranks. Use that when the data are symmetric about the mean. So let's say your data looks like this. So the student's t-test, right, assumes that your data are normally distributed. Okay, oof, some ugly normal curves. Let's say your data is not like that. Okay. Let's say instead your data are platykardic. So they're really flat. Okay. But let me extend this up a little bit. Nope. Easier this way. What's implied by the Wilcoxon is that your data don't have to be normal. They can be leptokurtic or platykardic, but the means are symmetric. Okay, then use the Wilcoxon paired. If they're not, if you just have kind of data that's all over the place, right? And this is true when you're doing behavioral experiments in particular. You can get really, if you're looking at activities and you're watching an animal that's either just gone crazy and playing or fell asleep, right? You'll get data that's can be something like this, right? And let's say like this. So in this, you would use a Sine rank test. Okay, Sine rank test. So this is where your data, we'd say the mean is here, right? It's pulled up away from these points by this outlier, right? So this box plot or the histogram would not, it would look like this. Have a really long tail, okay? So in that case, we're using the Sine rank test. So use the Sine rank test whenever your data are just poorly distributed, right? With lots of outliers and extreme measurements, okay? And just because you have extreme measurements doesn't mean you're stuck with the Sine rank test. Consider doing things like think about your data, think about the process that generates your data. And if it's something that occurs logarithmically or exponentially, consider data transformation, right? And things may look normally after being transformed. All right, so those are your classic tests. And just go through your head, memorize these, but remember what the assumptions are of each one. And if you know that, then you know the conditions under which you would use them. So on an exam, I'll give you some output and say, like, what test would you use? And I'll say, well, if it didn't happen this way, what test would you use? And so on. All right, the modeling approach is very different. So those tests I just went over, you're only asking, you're basically just testing the null hypothesis that there's no difference between groups. But if you're actually interested in the effect, you're going to take a modeling approach. And the model for two groups is Y, and then subscripts IJ, where it's the ith observation, and then the jth group. Okay, so J will just take on values 1 and 2. Okay, you're going to have an overall mean, and then you have a beta sub J plus epsilon ij. So there's going to be error for each group associated with each observation. Okay. So same sort of data. So this is our mean, this is our mean, here's our observations. And what you're saying is, I have an overall mean. Okay, that's going to be my alpha. So if you were to ignore groups, this is what it would look like. Right? So I'm just mushing these data together. Right? And there's alpha. So it's just calculated by the overall mean. And then there's the beta for group 1, right, will be negative. The beta for group 2, okay, will be positive. So this, a lot of times you'll see your betas don't have subscripts, and here you do. Okay, where you have a beta, and it just depends on what group you're in. Okay. And that'll just push you up or push you down. R does a weird thing where it actually holds one of these as your group, and then your beta is relative to the group. So usually if you have group A and B, it'll set the standard as A, and then your beta is an estimate of that group versus that group. Okay. So it's a direct measurement of the difference between the means. But the model itself is the overall average plus the group effect plus the error associated with it. And again, has a different use. You'll get out p-values, but your p-values are really related to beta. Okay, you'll get out a p-value related to your alpha, so you get an intercept, but that doesn't help you at all. The p-value associated with your intercept, well, most of the time, you know that your overall mean isn't 0, and the p-value you get out is that your alpha is different from 0. Okay, that's it. And that it really doesn't tell you much. What you're really interested in is your beta. Okay. And if you want to be slick, we learned about the likelihood ratio test, and you can actually test this model versus this model. So this would be an intercept-only model, even though it has the error, right? But we call it intercept-only because the only real effect you can really account for is the overall mean. So basically, it's comparing what if you include groups, does that help you, versus what about just identifying the overall mean? Is that a good predictor? Okay. All right. That's it. If you have any questions, please email me. But the important thing I would say in this thing is decide whether you are hypothesis testing, decide if you are hypothesis testing or not. And then if you are doing sort of classical tests, then look at the assumptions of your data. For the modeling approach, they're also the same assumptions as a student's t-test. And you can do a paired t-test. It's a little bit more complicated with the modeling approach. And we'll go over that in the future. Otherwise, that's all I got to say about that. And if you have any questions, send me an email.